For part 2 of this lecture about variability, I'm going to shift gears a bit now, and I'm going to talk with you about variance and standard deviation. These are two of the most fundamental concepts in statistical analysis. Most of what we do from here relies on either these concepts or it builds on them. I'm going to talk conceptually first and then go through the math. Look at these two data sets. The large dots represent the means for each data set. For the first data set, look at how far the points are from the mean. I put in lines to show how far the distance is from the mean. Now we're going to do the same thing for the purple data points. There's that distance, larger distance, and another larger distance. Those distances that I've represented with the lines are deviations from the mean. They're positive because they're simply distances. So we use absolute values. For example, the distance from 30 to 35 is a distance of 5. The distance from 35, which is the mean, to 40 is also 5. If we can get an average for the green deviations or distances, we have what is called the mean deviation. If we get an average for the purple deviations or distances, we have the mean deviation for that data set. You can see that visually the mean deviation for the green data set is going to be smaller than the mean deviation for the purple data set. Remember that one of the properties of a mean is that the sum of all those deviations would equal 0. So if we subtract each data point from the mean and try to average them, we can't do that. So we use absolute values for the deviations. But keep in mind that this makes intuitive sense if you remember that you're looking at distances from the mean. The distance is positive. Whether it goes below the mean or above the mean, the distance is still there. For example, the distance from 30 to 35, I've already talked about that. It's 5. It's the same distance as from 40 to 35. The mean deviation is not used often because using the absolute values also causes some bigger mathematical problems when we try to do analysis. So instead, so that we don't end up with a deviation that's negative, we actually square the deviations most often. And this is where we're getting at towards variance. We take the squared deviations and we add them all together so that we get the sum of the squares. So here on this number line, this data set, I've got one deviation of 5 from 30 to 35. I've got another one that's from 25 to 35. That's 10 squared. See, I square each of those distances or deviations. Look at the formula near the top of the slide. You've got your sigma, and then what that's saying is it's the sum of each of the deviations. So whatever the data point is, x, minus the mean, bar x, and squared. Key. It is not, I repeat, not the sum of all the deviations and then you square that. Don't get mixed up with that. You have to square each deviation and then add those together. So you can see at the bottom we've got 100 plus 25 plus 25 plus another 100. You get the variance when you find the average of those. So we sum them all up and then we simply divide them by the number of deviations we have. And in this case, the variance is 250 divided by 4, or 62.5. Notice a couple of things about the notation in your book. The author uses a lowercase x to represent the deviation from the mean. So there's two ways that it can be shown. You can take the value of x, xi means any value of x, minus the mean, or instead of writing all that out, you can simply represent it as a lowercase x, and the I just means any of them, any of those deviations. The second thing to notice is that the formula is slightly different when we are working with a sample than a population. The variance for a sample is slightly larger always than the variance for a population. Remember, when you take a sample, you can never be 100% sure that you're representing the entire population. So because the variance is larger, it actually allows for an unbiased estimate and makes the variance more likely to be accurate when we don't have all those scores of a population. Almost always we are working with a sample. It is so hard in statistics to get the numbers from every subject in a population. Last of all, notice the notation for variance. It's a lowercase s squared. That's the notation for variance whenever you see that. Make sure that you can compute the variance from both the squared deviations and from the raw scores. Those equations are in your textbook, and you'll be using those in the practice exercises. Now we have a problem with variance. It squares the units we're working with. Mathematically, it helps us to be able to do some analyses, but at the same time, it sometimes doesn't make sense. Let me give you an example. If this data set represents the minutes it took each student to complete a quiz, I have to say that the variance is in squared minutes. The variance for minutes to complete the quiz is 62 minutes squared. What in the world are squared minutes? Imagine you gave an IQ test and you're looking at the variance. It will be something like 225 points squared. That doesn't make any sense either. So we use the variance, but it's a problem when you start putting it in words and trying to make sense of it. So when we're talking about how far most of the scores are from the mean, we take the square root of the variance. Remember, the variance is the average sum of all those squares, but we take the square root of that to come up with the standard deviation. Then we can use original units, such as minutes, and we could say that the standard deviation is 8, roughly the square root of 62.5. It's going to be just under 8. 8, and then we're talking about minutes again. We don't have to worry about minutes squared or whatever, and it makes a lot more sense. As your book pointed out, a large standard deviation means large variability in distances from the mean. A small standard deviation means small variability in the distances from the mean. You can see how important standard deviation is in describing a data set. Imagine you have two data sets. They both have the same mean. Data set 1 has a mean of 39, data set 2 has a mean of 39. But you can see that data set 1 has a lot more spread in the scores than data set 2 has, because the standard deviation is 15 in data set 1, but it's only 4 in data set 2. A couple of last notes. You need to be able to use both formulas for figuring out the standard deviation, as well as be able to compare a large standard deviation with a smaller one. Also, please note that some authors use SD rather than a lowercase s to indicate standard deviation. And finally, be sure to read the section in your text about the shapes of frequency curves or distributions. A hint to remember whether it's positively skewed or negatively skewed. Look at the tail. You're looking for the long part of the tail. If the tail is long to the right, it's positively skewed or skewed to the right. In other words, there are fewer scores off in the right side. If the tail is long to the left, it's negatively skewed or skewed to the left. So look at the tail. That's the secret for remembering it.